Here in these flat, grassy fields is the natural habitat of wind turbines. Dwarfed by the open expanse, it is here that they harness one of the most useful resources on the planet, wind. Many species can grow to be over 200 meters tall, so Turbinus petalis has to keep a low profile. To conceal itself, it can fold its blades into a straight configuration.
Humans have been harnessing the power of the wind for thousands of years. The first recorded instance of using wind power dates back to the 1st century CE, with the engineer Heron of Alexandria's wind-powered organ. The Persians made the first wind-powered mills, using a vertical axis design as early as the 7th century CE. Windmills then spread throughout Europe from the 12th up to the 19th centuries, eventually being superseded by steam power. However, these designs were all inefficient at extracting power from flow. Aeronautical science advanced greatly in the 20th century, and from 1973 onwards, NASA's wind turbine project created a set of experimental turbines that paved the way for modern turbines. Wind turbines today play an important part in reducing our dependence on fossil fuels and mitigating the effects of climate change, and the UK is at the forefront of this, with the largest offshore wind power installations in the world. In 2018, the UK also went a record 55 continuous hours without coal since the Industrial Revolution, as a result of installed wind power capacity.
We're a group of 6 second-year aeronautical engineering students at Imperial College London, and for our applications exercise this year, we were tasked with creating a wind turbine to be tested at 4 different wind speeds, ranging from 6 to 12 meters per second. There were several design specifications that needed to be met. The tip speed ratio, or TSR, which is the ratio of blade tip speed to wind speed, needed to be between 3 and 8 when our power coefficient CP is at a maximum. This is the ratio of power delivered to the turbine to total power available in the flow, which in theory has a max value of 0.593, known as the Betz limit. However, the most important one was that the wind turbine needed to be printed in one piece into a box of 400 by 150 by 75 millimeters.
The first thing we had to do was decide on the number of blades that we'd go for. There was very little time for us to come up with design considerations, so we had to make sure we chose a reasonable design and committed to it. We ended up choosing to use 3 blades since it has a high ceiling for coefficient of power in the limited range of TSR that a turbine has to operate in. 3-bladed wind turbines also have the distinct advantage that the blades don't experience symmetric forces, which mitigate against resonance and therefore rapid unscheduled disassembly of our wind turbine. We also chose a small diameter of 250mm, with the idea that recirculating airflow would cause drag in the blade's most important section, its tip.
Our first challenge was to design a turbine that could be printed in a one-piece configuration, yet still be 3-bladed and of an appropriate diameter. Our solution to this was to incorporate a semi-concealed hinge into the nose cone, and thereby split the nose cone into thirds, each third having 1 blade, that would eventually secure together with bolts. The hinges were designed to have alternating male and female ends either side of the nose cone thirds, and these were designed to be printed in an assembled configuration as one piece.
Ideally, a successful design means that the turbine's actual performance will be very close to its design point. Thus, the TSR at maximum power had to be predicted as accurately as possible.
We used the blade element momentum theory to calculate the thrust and power for different settings of wind speed, rotation speed, and pitch angle, allowing us to simulate the turbine's performance and estimate the design point. The standard 1D momentum analysis presents some oversimplification of the flow behavior, but these were mitigated by applying 2 correction factors. The Prandtl tip loss factor corrected the assumption of an infinite number of blades, and the Gloret correction dictated an empirical and more realistic relation between the thrust and the actual flow induced by the rotating wake. Everything was implemented in MATLAB code, and the final TSR of 4.5 was decided.
As you move from the root of the blade to the tip, the local blade speed increases. However, the incoming wind speed is constant throughout the blade, so the blade needs to be twisted in order to vary the local angle of attack. The angle of attack decreases to ensure that stalling does not occur at the tip. We compared the Betz and Schmitz formula for determining the optimal pitch and chord angles as you go along the blade by plotting graphs using MATLAB. Even though the 2 graphs are very similar to each other at the tip of the blade, we decided to use the Schmitz formula as it uses a more rigorous proof. It uses the conservation of angular momentum, where the torque in the shaft is generated by the vorticity of the wake.
After taking this data, we then needed to evaluate if the turbine would be able to handle the structural loads imposed on it. With an increased number of blades, achieving the optimal blade area requires that the thickness must decrease. If unaccounted for, this pursuit of maximum aerodynamic efficiency could not only lead to a structurally compromised blade, but one with excessive deflections that would break some of the fundamental assumptions that we use to analyze its aerodynamic properties. For this reason, we wrote code based on simple bending theory that we learnt in first year, extended for continually varying area and second moments of area. As you can see from the results, the tip deflection under maximum load is 8mm, and the peak stress is well below the failure stress for ABS plastic.
The next step for us is to choose which airfoil to use. We chose those for the small wind turbines only. These airfoils were imported into Q-Blade for further analysis on CL versus angle of attack and maximum liftover drag. The SG6043 was chosen at the tip of the blade because of its high CL and highest maximum lift-to-drag ratio of all the airfoils we could choose from. While the SG6040 was chosen at the root because of its higher thickness-to-chord ratio, which gives a better saw characteristic and a stronger structure. The wind turbine was then simulated in Q-Blade to check against our calculations. Creo was then used to cut up our design. The blades were produced by blending 20 sections of linearly interpolated airfoils, chords, and twist angles produced by a MATLAB script.
The first question that came up when designing the blade tips was whether or not we should add a winglet. After reading a few papers, it became clear that at low speeds, a winglet would bring about a 2 to 3% increase in power, which would mean our turbine would get more bang for the same buck. As the margins between each team will be very small, a 2 to 3% increase in power could be crucial in gaining marks for performance. After finally deciding to add a winglet, the next challenge became its design: the twist, toe, sweep, and cant. For the sake of simplicity and to reduce the time spent on Creo, the twist and toe were set to 0 degrees. For the sweep and cant, most papers agreed on 45 degrees for both, with the cant angle positive in the downstream direction.
To the winglet, we added a central section which curves like a falcon's wing, which also flies at similar Reynolds numbers to our blade tip. The first step in manufacturing was to make our hub. An aluminium blank was loaded into the CNC lathe. The blank was then roughed out to diameter and an end mill was used to create the interior hole in the hub, instructed by a G-code that we entered into the machine. You can also see the cutting fluid running through the end mill, which is used for lubrication and cooling. Next, the blank was loaded into a CNC mill, and an end mill was then used to create the flats on the hub 60 degrees apart. The M5 hole for the set screw was then drilled and tapped. The hub was then cut free from the blank using a separate lathe. The edges were also then deburred, to remove any sharp edges left over from the machining processes. Finally, the keyway was broached into the hub using a hydraulic press and our hub was complete. We then received our turbine from the 3D printer. Unfortunately, the face-to-face tolerance on our hinge was barely too small at 0.2mm, so one of the hinges broke off. Fortunately, we were able to glue it back together later. We then sanded our turbine down to remove 3D printing layer lines. Water, along with sandpaper of increasing grit, was used due to the fact that we could have more control than with using acetone smoothing. Due to the fact that our layer lines ran longitudinal to our blades, minimal sanding was needed. Finally, the turbine was glued together, with the excess sanded and filed off. The hardware was then inserted and our manufacturing was complete.
Finally comes the time to test our turbine. The testing took place at the Donald Campbell Tunnel. The wind speed would gradually increase and measurements were taken at speeds 6, 8, 10, and 12 meters per second. The turbine didn't self-start, but after a slight kick was given to it, it went on a steady rotation, successfully maintaining both its structural integrity as well as a steady power production. No instabilities or resonance was observed, although a slight buzz could be heard about 11 meters per second. The turbine wings can be seen deflecting a little bit backwards towards the tips. Maximum power is generated at RPM of 2400 and a wind speed of 12 meters per second. A TSR of 5.5 obtained, corresponding to a CP max of 0.41. This was fairly away from design point, but this could be attributed to the blockage effect that 14.2% of the tunnel area was covered by the turbine, leading to higher effective incoming wind speed. For normal wind tunnel testing, a guideline of 2% tunnel area is used. Overall, the turbine did not fail and produced a satisfying CP, which means our application exercise was successful. All manufacturing requirements were met, and the advantages of 3D printing and of ABS plastic were greatly exploited. As for the winglets, unfortunately, due to a lack of time, we did not have the time to redo the testing with the winglets cut off in order to assess their contribution to the overall performance. The turbine did not self-start. However, this could be achieved by increasing the twist at the root or adding paddles at the tip, although this would add drag and compromise its performance in the design regime.